Let w equal f of x and y, where f is a differentiable function of x and y. If x equals some function of t, and y equals another function of t, where g and h are differentiable functions of that variable t, then w is a differentiable function of t. And our formula for taking the derivative of w with respect to t would be taking the partial derivative of w with respect to x, and then taking the derivative of x with respect to t and multiplying them. The lowercase delta here, that represents taking the derivative of a function with respect to one of multiple variables. The English d means that, say, your variable x would only have one variable t. And that's what we're talking about here. W would be defined as a function of two separate variables, or at least two variables, and then each one of those variables are defined by another variable. Let's move into an example and we'll check it out. Let's let w equal x squared y minus y squared, where x is equal to sine t, y is equal to e to the t, and we're going to find the derivative of w with respect to t when t is 0. Okay, so following the format up here in the theorem, we have the derivative of w with respect to t is the partial derivative of w with respect to x times the derivative of the x with respect to t, plus partial derivative of w with respect to the y variable times derivative of the y with respect to t. All right, this first part, the derivative of w with respect to x is going to be 2xy 0, so 2xy. dx dt, that's this part, the derivative of x with respect to t is cosine t. Derivative of w with respect to y, that's going to be x squared minus 2y times derivative of the y with respect to t. Derivative of e to the t is still e to the t. Cleaning that up a little bit, also because ultimately we want our variable to be in terms of t, our function w's derivative in terms of t, I'm going to replace x with sine t, so 2 sine t. Y is getting replaced with e to the t, so 2 sine t e to the t times cosine t, plus x squared would be sine squared t minus 2 times y, that's 2 times e to the t, and those x and y's being replaced are still multiplied by e to the t. Distributing and cleaning up, we have, and a little bit of reordering, 2 e to the t sine t cosine t plus e to the t sine squared t minus 2 e to the 2t. Now when you sub in a 0, sine 0 is 0, so that eliminates that first group. Sine squared 0 is 0, that eliminates the second group. It's this last bunch. 2 times 0 is 0, e to the 0 is 1, times negative 2 is negative 2. Two objects are traveling in elliptical paths given by the following parametric equations. The first object is moving with these x and y components with an underlying variable of t. The second object has x and y components given. At what rate is the distance between the objects changing when t equals pi? Well, let's write down the distance formula. This is the distance excuse me. Also, when t equals pi, going back up to these parametric equations, substitute pi into all four of these. x1 is 4 cosine pi, which is negative 4. y1 is 2 sine pi, which is 0. x sub 2 is 2 sine of 2 times pi, that's 0. And y sub 2 is 3 times cosine of 2 pi. Cosine of 2 pi is 1 times 3 is 3. The distance at pi, when t is pi, can be calculated by x2 minus x1, that's 4 squared, 16, plus y2 minus y1 squared, that's 3 squared, 9, 16 and 9 make 25, and that has a square root of 5. We will be needing this value repetitively. Okay, so let's go in here. The derivative of distance with respect to x1. This is not the easiest thing to find. In fact, you need to think of this as all that stuff written to a 1/2 power. Change your radical to a power of 1/2. Now by chain rule, that's 1/2 times all this stuff underneath to the negative 1/2. When that's moved to the denominator, it turns back into square root of all that stuff. So this 2 is part of the 1/2. Moving all that stuff to the denominator makes it a power of positive half, and that can be rewritten as a square root. So that denominator is going to be in common with all 4 of these partial derivatives. Underneath, since we're taking with respect to x1, this is going to be 2 times x2 minus x1, 2 times x2 minus x1, times the derivative of x1, which is a negative 1. That's why there's a negative there. Okay, these 2's will cancel, so remember the distance was 5. That's why there's a 5 in the denominator. The 2's cancel. This has a value of 5. So we have a negative after the cancellation. We have a negative 1. x2 minus x1, that is 0 minus negative 4, which is 0 plus 4. Grand total, negative 4/5. The derivative of the distance formula with respect to y1 is going to be much like this one. The denominator will be identical because it's 1/2, all the stuff underneath to the negative half. Transfer it to the denominator. This 2 is from the 1/2. Everything goes back under the radical. Underneath, focusing on the y1 term, this part will be 2 y2 minus y1. Derivative of y1 is negative 1, and so there's a negative. The 2's cancel, so we have negative 1/5 y2 minus y1, that's 3 minus 0, so negative 3/5. We're going to need all these values on the next slide. Continuing with our derivatives, partial derivative of s with respect to x2, again 1/2, all that distance formula to the denominator to the 1/2, square root it. With x2, we're going to have 2 times x2 minus x1. Derivative of the x2 term is positive 1, so there's no negatives on these. We're going to take these 4 values and go on to the next slide. Okay, so recall the x1, x2, y1, y2 from the previous slide. If you need to rewind the video a little bit to have those, or you can look, this same set of pages are in your Google Drive folder. Anyway, the derivative of the x1 parameter will be negative 4 sine t. Plugging in pi, we get 0. The derivative of the y1 parameter is 2 cosine t. Substituting in pi, that's going to be a negative 2. Cosine of pi is negative 1. Derivative of the x2 parameter with respect to t, we get 4 cosine 4t. Don't forget to use chain rule. Subbing in pi, 4. And then finally, derivative of the y2 parameter, negative 6 sine 2t. Sub in pi, sine of 2 pi is 0, 0 overall. Now, the values that were really hard to get on the previous slide In combination of these four values that we just got, we can find the derivative of derivative of distance with respect to the variable t using all these expansions. All these partial derivatives are from the previous page. All these with the English D we just got up here in the top section of this slide. For previous slide, this slide. Be very careful subbing in. Previous slide, this side, and so forth. Grand total, the first and fourth terms go to 0, so the grand total here in the middle is 22/5. And that is the rate of change in the distance between the objects at t equals pi. Another example, find the partial derivative of w with respect to s and partial derivative of w with respect to t when w equals 2xy. X is defined as s squared plus t squared, and y equals s over t. Now this time, each function, x and y, have two variables, but let's do them by substitution. Okay, so w is 2 times x times y. That's 2 times s squared plus t squared times y, which is s over t. So 2 times x times y. Distributing, that's 2s cubed over t plus 2s t squared over t. T goes into t squared t times. So be very careful distributing. From here, what we've done is we've changed w from x to y into terms of s and t. Now we can take these partials. The derivative of w with respect to s, starting from here, not up here, with respect to s is 6s squared over t plus 2t. This answer is totally fine. If you wanted to make a common denominator, you've got to give another t top and bottom. And so you'd have one fraction. The partial derivative of w with respect to t, again from here, will be, you take this up, it's t to the negative 1. So its derivative will be negative 2s cubed t to the negative 2. T to the negative 2 can be dropped back down to the denominator, making it t squared, plus derivative with respect to t will be 2s. And we can use the same trick. This answer is totally fine. Or if you wanted to make this a common denominator, give this second term a t squared top and bottom. And also I reverse the order. So it's 2s t squared minus 2s cubed all over t squared. But again, this answer is totally fine. Now let's officially look at how to do those without substitution. Let w be a function of x and y, where f is a differentiable function of x and y. This time x, instead of being only g of t, it's g of s and t. It's two variables underlying, such that all first partials exist. So dx ds, dx dt, dy ds, dy dt all exist. Then here's the expansion for derivatives with respect to s and t, which are the underlying variables. We take the derivative, it's going to be the partial derivative of our function with respect to x, times the derivative of the x part with respect to s, plus partial derivative of w with respect to y times derivative of the y function with respect to s. Similarly for dw dt. Let's jump right into an example. This one looks very familiar, as it should. The derivative, we're going to define w again as 2xy. X is defined as s squared plus t squared. Y is still defined as s over t. On the previous slide, we just substituted s squared plus t squared into x. S over t went into y. And then we took our partials. Again, that was the example we just finished. Using this theorem and the expansion, the derivative of w with respect to x is 2y. The derivative of x with respect to s is 2s. Derivative of w with respect to y, that's 2x. Derivative of y with respect to s, that's 1 over t. Cleaning it up for, I'll tell you what, let's go ahead and substitute. Replace y with s over t, so you get 2s over t times 2s. X replaced with s squared plus t squared, so that's 2 times s squared plus t squared times 1 over t. Be very careful here, that's 4s squared over t plus 2s squared over t plus 2t squared over t, which would be this part. Common denominator of t, add like terms, that's 6s squared plus 2t squared all over t. Then if we take the partial derivative of w with respect to t, here's our expansion. Again, that's from the theorem above. Derivative of w with respect to x, that's still 2y. Derivative of x with respect to t is 2t. Derivative of w with respect to y, that's 2x, same as it was in part A. Derivative of y with respect to t, move the t up so it's st to the negative 1, and then when you take your derivative, it's negative st to the negative 2. Drop your t back down, it becomes t to the positive 2. Y replaced with s over t, so 2 times s over t times 2t, plus 2, replace your x with s squared plus t squared times negative s over t squared. Be very careful here, this is 4s, the t's cancel, minus 2s cubed over t squared. And you can also negate here, but you'll drop your parentheses if you do. If you group in parentheses, only use the negative once. If you distribute and wanted to spread it out already, then no parentheses and put a negative here. That second distribution, the t squareds cancel, and so it makes it 2s. I went ahead and wrote them in here to make it a little easier to get a common denominator. 4s, if you put a t squared in the bottom, you got to give it a t squared up top. So it's 4s t squared over t squared. And then I went ahead and distributed the negative sign. Hindsight, I should have done it here, but I just didn't. Fraction, fraction, both negative. This answer is totally appropriate, but if you notice like terms in the front and the back, that's 2s t squared minus 2s cubed over t squared. If we have a function of multiple variables set equal to 0, now this will make life a lot easier than those. Well, I lost my train of thought. Let me start over. Let's take a function of x and y, and we're going to put it equal to 0. If you run across a problem in your homework where it's not equal to 0, set it equal to 0, and then that's your function. If your function defines y implicitly as a differentiable function of x, then dy over dx is equal to the negative partial derivative of x with respect to x over partial derivative of f with respect to y, as long as that bottom partial derivative isn't 0. If you upgrade to a three variable function, f of x, y, and z, again, make sure everything's on one side and it's equal to 0. If that function defines z implicitly as a differentiable function of x and y, then the partial derivative of z with respect to x is going to be negative partial derivative with respect to x over partial derivative with respect to z. This looks really messy, but actually they just trade places. Like up here, the x winds up being on top, the y on bottom. Same thing here. Partial derivative of z ends up being on the bottom, and x goes on top. Let's go into an example. We're going to find dy over dx for this function. This would be your capital F of xy. Note that it's set equal to 0. If that's the case, take everything from this side, and that's your function. The derivative of that function with respect to x is 0, 0, 0, negative 2x, and 0. The derivative with respect to y is 3y squared plus 2y minus 5, 0, and 0. Now, remember to flip them. The negative of negative 2x, which is going to be a positive 2x, over, then the y goes on bottom, 3y squared plus 2y minus 5. And let's do one more example. This time we're going to do it with a 3-variable equation. We're going to find the partials of z with respect to x and y. This is the equation given. Note the 5 isn't on the same side as everything else, so move that over. I made a little note here to make sure you get an equals 0 in the original equation. Once you do, your function can be set to all those terms that are equal to 0. Partial derivative with respect to x, that's 6xz minus 2xy squared, 0, 0, 0. So you just have a couple terms. Go back through, partial derivative with respect to y, 0, negative 2x squared y, 0, plus 3z, and 0. You don't have to write the zeros, just only what is non-zero. And then finally, the partial derivative of f with respect to z, 3x squared, 0, 6z squared, 3y, and 0. So that gives us 3x squared plus 6z squared plus 3y. This partial derivative, we're going to have f of f sub z. That's going to go to the bottom. So these three terms are your denominator. The negative of f sub x, so that's the negative of this partial. Distributing the negative, rearranging terms, 2xy squared minus 6xz all over f sub z. The partial derivative of z with respect to y is negative f sub y over f sub z. F sub z, these three terms again, that's your denominator. Negative derivative with respect to y, those go in here. Be sure you change signs as you distribute. And you're welcome to rearrange the terms. Just be careful with your signs. So that's 2x squared y minus 3z all over f sub z. And these are your partial derivatives when you have an equation and the variables are defined implicitly. It takes a little bit to get used to the chain rule with multiple variable functions, but just keep practicing. Look inside your homework. I tried to pick some with watch it videos as well, so that on top of these YouTube videos, the publisher's videos hopefully can help you out. And as always, swing by the office, email, phone call. If something comes up, let me know, and I'll do my best to help you out. That's all I ever want, is to help everybody succeed. So anyway, y'all have a good one, and I will get back with some more videos.